Oh, because he's in California. This
Good afternoon, everyone. Can you hear me? Just by indication, either thumbs up. Can you hear me?
the one. This is the third one.
Mr. Mandela, your mic is still on.
Yeah. It's not. Why it is taking I mentioning anything it's put me they are not going to earn TV come around.
Mr. Mandela, your mic is still on. The rest of you guys, can you hear me? Just a thumbs up is fine. Okay. Thank you. Okay, can you see my screen? Because I'm going to start now. Okay. Doing a few problems on simple harmonic motion. I just want to check something.
It was quiet.
Okay. Starting with problem number 6. I don't know if you can make out the words, but you guys are joining on Teams, so let's see if it's worthwhile. I'm just placing the stuff on my desktop so I can see myself. Okay. So, can you guys see my screen that I'm sharing currently? Just a thumbs up so I can start. I want to know if you can see my screen. It currently has the number 6 written on it. Anyone, can you see my screen? Okay, thank you, Caesar. So, let's start. Simple harmonic motion. Okay, the problem says a body, we have a body. Okay, it's oscillating with simple harmonic motion along the x-axis. Its displacement varies with time according to the equation. So we have an equation for the displacement, meaning the position of this body. Okay, and it is varying according to this formula 5 comma 0 cosine of pi times t. Okay, let me see if you guys can see that. Okay, cool. So its position is varying on the x-axis according to this formula. Now they ask us, what is the magnitude of the acceleration? What's the magnitude of the acceleration? So they want the acceleration of the body at t equals 1 second. Okay, so they want the acceleration at t equals 1 second. So they want the acceleration at t is equal to 1 second. Okay, how do we get the acceleration? Okay, so this is the position. Okay, the position. How do we get the velocity? From position, we can go to velocity. Velocity is just the time derivative of the position, meaning it's just d dt of 5. Okay, this is not 50, it's 5.0 of 5. I'm not going to write the 0.0, it's just 5 cosine pi theta. That would be your velocity. Okay, that's your velocity. Let's continue. If you find the derivative of that function, the 5 is a constant, so it comes out. The derivative of cosine is equal. I just want to check something here. Okay, you can see me. So the derivative of cosine is negative sine. So it's negative sine. That's the derivative of cosine pi theta. And then you differentiate whatever is inside the bracket. Okay, the derivative of pi t is just equal to pi. Okay? So it's 5 pi, let me just write it this way, times pi. Okay? That is the velocity in terms of t. Now what is the acceleration now in terms of t? Acceleration is just dv dt. It is the time derivative of the velocity. Okay, so it's d dt of negative 5 sine pi theta times pi. Okay, if you find its derivative, we have the acceleration. And if we were to find that the acceleration there, 5 is still, negative 5 is a constant. The derivative of sine is cosine pi t. And then derivative of pi t is just pi, so it's pi squared. Okay? So there we have it. That is the formula for the acceleration of this function that has been given to us. Let me just clear this and rewrite it. The acceleration of this function in terms of time is equal to negative 5 pi squared times the cosine, I almost wrote sine, times the cosine of pi times t. And that ladies and gentlemen, is the formula that we are currently working with. Okay, that is the acceleration of this particle on the x-axis. Okay, now they asked us to find it after 1 second. So let's plug in 1 where we see t. It's negative 5 pi squared cosine of pi times 1. Now the cosine of pi, that's negative 5 pi squared cosine of pi. The cosine of pi is negative 1. So it's negative 5 pi squared times negative 1. That just gives me 5 pi squared, which is approximately 5 pi squared is approximately 49,34 meters per second squared. Okay, that is all that is to this problem. You were given the position in terms of time. You just had to find the acceleration, and you do that by just constantly differentiating. Okay, let's move on to the next problem. Is there any questions? If you have any questions, you can ask now, but it's a relatively simple problem. If there's any questions, feel free to ask and I will explain again. Let me just do it like that. Let's say we have a body. Now the next problem is a body oscillates with simple harmonic motion along the x-axis. Its displacement varies with time according to the equation. So when again we are given an equation that describes the displacement over time, and that displacement is 5 sine of pi times t plus pi over 3. Okay? That's what they give us. The phase in radians of the motion at t equals to 2 seconds is. So, first of all, what do they want? They want the phase. Okay? The phase in radians after 2 seconds. Okay? So basically what you do is this here will constitute your phase. Okay? That will constitute your phase. So let's say the phase is equal to pi times time plus pi over 3. If you were to plug in 2 seconds there, pi over 3, that's 2 pi plus pi over 3. 2 pi plus pi over 3. Now, you can do just the old way of adding up. Okay, 2 pi is just 6 pi over 3 plus pi over 3. The denominators are the same, so it's 7 pi over 3. 7 pi over 3 is the phase, and that is the correct answer. Moving on. Is there any questions? If you have any questions, these are just simple plugging and playing. Okay? If you have any questions, you can ask now. This is actually very simple. It's just going to be probably about 10 more minutes. So, let's see. The next question. Now, they don't have the pictures there, but this is what the question should look like. Question number 8. The question is as follows. They ask us, or rather they ask, if this, and I'm going to draw it because they don't have, let's say this is a wave. Okay, this is time, this is y, that is a wave. Okay, they ask us, or rather they ask in this question, This is the sine wave at one point of a string as a function of time. Okay, so this is what should there be, what should be in that figure there. 16.1. So now they ask you, and they don't have the rest of the picture, so you can't make a choice, but I can tell you that they ask which of the graphs below shows a wave where the amplitude and the frequency are each reduced in half. Okay, so where is the amplitude reduced in half and the frequency is reduced in half? So if we reduce the amplitude, this, in half, the distance from there to there would be halved. Okay, because that is the amplitude, it's the distance between the highest point and the lowest point and the equilibrium. Okay, so if we were to reduce the amplitude by half, the wave would be smaller. Okay, so if we were to reduce the amplitude by half, the waves would be smaller. But we also have to reduce the frequency. Now, frequency is the amount of waves in one cycle. Okay, so if we reduce the frequency, it means the number of waves per cycle gets less. Okay, so this is the original graph. Okay, now let's reduce firstly the frequency. If we reduce the frequency, okay, this wave would be cut off. If we halve the frequency, the wave would be cut off right here. Okay, where I've drawn that line, that's where the wave would be cut off. So the wave would look something like this. Sorry, let me draw it again. So it looks something like this. That's what the wave would look like. But remember, we are also halving the amplitude. We are halving the amplitude. So the actual answer would look like this. The amplitude would be halved and the wave's frequency would be halved. So this, unfortunately, we don't have the, what's this time? The drawings there, or the pictures does not show for some reason. It is not showing, but that is what it should look like. Okay, and of course if you have questions, it seems like there's no questions, you can ask now. Question number 9 has to deal with, correctly, if you have read it, it deals with gravitation. Now they have a problem. Okay, a 50 kilogram satellite circles planet Crouton every 5.6 hours in an orbit with a radius of 12 million meters. Okay, now what is the magnitude of the gravitational force on the satellite by planet Crouton? Okay, so we have a satellite that's orbiting a planet every 5.6 hours, and this planet has a radius of 12 million meters. I almost said miles. Now, we know that the force of gravitation in this case is also equal to the centripetal force, which is equal to mv squared over r, the radius. Okay, where v is the velocity. So first let's calculate v. V is equal to, if you remember circular motion, v is equal to 2 pi r over the time it takes, the period. Okay, so if we have the velocity, we can say 2 times pi times r, which is the radius, and in this case it's 12 million meters. 12 times 10 to the 6 meters, that's meters up there, over the time, and that will give you the velocity. The time it takes is 5.6 hours. Now if we convert 5.6 hours to seconds, it becomes 20,160 seconds. That's the amount of seconds that there are in 5.6 hours. Now, if you were to work this out, we get a nice answer of 37,000 or 3,749.3 meters per second. This is how fast this satellite is orbiting the planet Crouton. Okay, this is how fast this satellite is orbiting the planet Crouton. Now, we have the velocity here. We just worked it out. But they are not asking for velocity, they are asking for the force on this satellite. So, the force is equal to the centripetal force, which is mass times velocity over the radius. Now the mass, they tell us, is of the satellite is 50 kilograms. The velocity we just worked out is 3749.3 meters per second, and we square that over the radius of 12 times 10 to the 6 meters, giving us a gravitational force of approximately, we can say approximately, but it's around this number, of 58.6 newtons. This is, it's going to be kilogram meter per second squared. That is the Newton. Okay, so 58.6. And you'll see here that it is indeed 58.6 newtons. Now, second to last question. They ask, a satellite is in a circular orbit around the Earth at an altitude which is at which air resistance is negligible. Okay, so there is a satellite orbiting the Earth at a distance such that air resistance is negligible. Now they ask us, which of the following statements is true? Okay, we are going to write down all the statements that are true. Number 10, there is only one force acting on the satellite. Yes, that is a true statement. Okay, gravity is acting on the satellite. It's in conceptual free fall since there is no air resistance, there is no friction. And the satellite is not connected to another something, so it is only one force. There are two forces, no, two forces, no, three forces, there's only one satellite, so A is the only correct one. There's only one force acting on the satellite. Okay, now let me go to another problem which should actually have, or should have been part of this section. An interesting problem that I got the last time, but I've decided I'm going to do it. Let's say the amplitude. Let's say the amplitude of a system moving in simple harmonic motion is doubled. Okay, so we are doubling the amplitude of a simple harmonic system. Okay, determine how does the total energy change, the maximum speed change, the maximum acceleration, and the period. Okay, now there are all the answers. Let's see if we can get it. Now the maximum, the first one is, let me just get, just get one of my notes here. Okay, there we have. Okay, so the total energy. How do we calculate the total energy of a simple harmonic oscillator? If you're a VV student, by the time you watch this, or maybe you have find it already, but if you are a VV, we will get to this. But the total energy of a simple harmonic oscillator is equal to a half spring constant times the amplitude squared. That's the energy of a simple harmonic oscillator. Okay, now they tell us we are, this is the spring constant, this is a half a constant, and that's the amplitude. Okay, now let's double the amplitude. Okay, a half times k times 2 2 times the original amplitude. Okay, that gives us 2 times a half times k times amplitude, and this here altogether is just the energy, the original E. See, this was original E, so it is just 2 times E. Okay? But I did miss something. I forgot to add the square. Okay, so let's see how that changes. I forgot to add the square there. I just checked on my notes. So we add the square. So this 2 squared becomes 4. A becomes A squared. Okay. So it is just 4 times the energy. So the total energy quadruples. If we double the amplitude, the total energy quadruples. Because energy is, and you could have seen this straight off the bat, energy is directly proportional to the square of the amplitude. Okay, you could have just done that without using actual formulas, but I prefer this way. So this is what happens to the energy. It quadruples. The energy increases by a factor of 4. Let's go B. What happens to the maximum speed? In order to say what happens to the maximum speed, we need to know how to calculate the maximum speed. Now the maximum speed, or V, is equal to angular acceleration times the amplitude. Now they tell us that we are currently doubling the amplitude. So what if we were to double the amplitude? So if we double the amplitude, the new speed to amplitude, that is just 2 times angular speed times that, and we know that that is just the speed, the maximum speed. So it's just 2 times the maximum speed. So if we were to double the amplitude, the maximum speed doubles, and that is what the answer says there in number 2. The maximum speed then doubles. Number C, if we double the amplitude, what happens when to the maximum acceleration? What is maximum acceleration? The maximum acceleration or acceleration is equal to angular speed times the amplitude. Let's double the angular speed. Double it. Take the 2 to the front. We have there. We see this is equal to the angular acceleration. So the angular acceleration doubles as well as the angular speed. And you could have just seen that by knowing that angular speed is proportional to the amplitude, while angular acceleration is also proportional to just the amplitude. Finally, what happens to the period if we double the amplitude? The period is 2 pi. This is what you've done in the mass times k. A similar one you've done for the pendulum, which is just based on the length and the gravitational acceleration. So this is period. Okay, if we doubled the amplitude, you'll see here the period is only based on the mass and the spring constant. Okay, so if we were to double the amplitude, the period would stay exactly the same. The period t would not change. Okay, t would not change. T the period will not change. The period will not change if we double the amplitude, as the amplitude has no effect on the period. Now, ladies and gentlemen, I am going to say, for those FVV students, I'll see you tomorrow. For PHYV students, I hope that it is very fast because it's quite easy. Or maybe I'll just ask maybe if it was informative or anything. So, that is all that we have time for today. I will see you next week. Please join James or Arnold during the course of this week. And I'm going to say goodbye.